So we will continue. So the components that you saw with the asterisk are what we call as the reaction intermediates. So when we speak of reaction intermediates, so these are the different reaction intermediates which you would be able to read from our reference book, that is Levenspiel. So they can be free radicals. So these are free atoms or larger fragments of stable molecules that contain one or more unpaired electrons. So they are generally unstable and highly reactive, and the free radical is designated by a dot on its chemical symbol. So whenever you see in a reaction mechanism a compound which has a dot after it, then that's an intermediate, specifically a free radical. Now, another form that your intermediates can have could be in the form of ions and polar substances. So ions meaning they are electrically charged atoms or molecules or fragments of molecules that act as active intermediates. So these ions and polar substances. Now you see them with, of course, the minus or the plus sign. So they are intermediates as well. Now we can also have molecules and transition complexes. So these transition complexes are actually strained bonds, unstable form of molecules or unstable association of molecules which resulted from numerous collisions between reactant molecules. So transition complexes, so they readily decompose and form the final product or products. And in terms of, so those are the intermediates, the different forms of intermediates for your mechanism of reaction. They will appear in the mechanism of reaction for non-elementary reactions. Now, for mechanisms, we can also have what we call reaction schemes. The first one is the non-chain reaction. So in this particular type of reaction, or reactions, the intermediate is formed in the first reaction and disappear as it reacts further to give the products. So we are still referring to non-elementary reactions in which we have a series of reactions to follow how the products came about from the reactant. So it's just a two-step reaction in this case, non-chain reactions. Okay? Or it could be several steps as long as the intermediates are disappearing right away or decomposing right away to further give way to the final products. So the first reaction is in the formation, the formation of the intermediates, and the last would be the formation of the products from the decomposed intermediates. Okay, second one would be the chain reactions. So the intermediates in this case, or the intermediate is formed in the first reaction called the chain initiation step, combines to form product and more intermediates in the chain propagation step. So propagation in the sense that you have more intermediates being formed. And in the last step, it is destroyed in the termination step or the chain termination step. So as an example, you have this. So initially, you have the formation of the intermediate. Then the intermediate reacts with more of the reactants and forms more intermediate. And now you have initially the formation of the product. So the one that is being propagated here is the intermediate. Then the final step is the termination. So the produced intermediate now decomposes to form the final product. There are only two schemes actually, the non-chain and the chain type. Most of the type we have this one, the chain type of reaction mechanism. Now, in the propagation step, the intermediate is not consumed but act as a catalyst for the conversion of the material to the product because you already have here the product. But the first formation of the intermediate here is for this intermediate to act as a catalyst for this reactant to form the product. Once it's there already, you have more of the reactants. These intermediates decompose finally to form the final product. Now we have a sample problem here. Hopefully we can finish this before the time. So I have 15 minutes, I can finish this. So I will just go to the whiteboard and show how this is done. But before that, let me read. So this is taken from Levenspiel, and I have chosen this because this will illustrate how the particular mechanism will substantiate or prove that the actual reaction is a first order decomposition of dinitrogen pentoxide. So show that the following scheme, so this is your reaction mechanism, proposed by Og, is consistent with and can explain the first order decomposition of dinitrogen pentoxide. Okay, this one. So this is your given. I will rewrite it so that we will have something to follow through in the process of proving. So we will now be proving that this is the mechanism for the first order decomposition of dinitrogen pentoxide. Okay. So your first reaction is actually, sorry. Why am I? Let me share again, class. This is the original mechanism. I'll write it here. So this is our mechanism. Whenever you see a reversible reaction, there's a need for you to break down the said reaction into two separate reactions. So your forward reaction and your reverse reaction. So your rate constant here is K1, your rate constant here is K2. So you have now 4 reactions, all viewed as elementary, as dictated when you do the proving that your mechanism is actually a series of elementary reaction. Now, since we're going to prove that the decomposition of dinitrogen pentaoxide is first order, this must be the rate law. Sorry. This must be the rate law that we are associating or correlating with this particular mechanism. So we have K, then we have N2O5. I will just write concentration like this, okay? So this one tells you that the rate law or the rate of reaction of dinitrogen pentaoxide is first order because the exponent of the concentration of dinitrogen pentaoxide is 1. So we are to prove that this broken down reversible step, the first step, the third and the fourth step is the appropriate mechanism for this first order decomposition. So the first step that you will do always whenever you see a reversible reaction is you have to write it in its equivalent non-reversible reaction. And this would be the representation. The next is you are to write the net rate equation based on the species that you are to prove the rate of. Since we are to prove the rate of dinitrogen pentaoxide decomposition, so the net rate equation would be based on the initial net rate equation will be based on this particular component. Okay, now why I say it's the net rate equation, because all the equations here that you have the four, you are to write the corresponding rate law if they have the presence of dinitrogen pentaoxide. What do I mean? In the first step, in the first reaction here, I don't see any dinitrogen pentaoxide, so it won't be written in my rate equation. But in the second, in the reverse reaction, I see dinitrogen pentaoxide as a product. And since I've started with writing a negative here, meaning it's a reactant, the way I will write this one, the second step in my rate equation, the net rate equation based on dinitrogen pentaoxide would be this. It would be negative K sub 2 times the concentration of NO2 times the concentration of NO3 asterisk. Why am I rating it as negative? Because in the first place, I have already started with a rate expression that makes N2O5 a reactant, but it's a product in here, so it should be written as negative. Now, I don't have N2O5 here. I don't have N2O5 here. So meaning this is my net rate equation based on N2O5, and this would be my equation 1. Now, whenever you have written already the net rate equation for the species that you are going to prove the rate law of, and you see concentrations of intermediates, this one, you see NO3 here, that would be the next net rate equation that you will set up. So if this is an intermediate, if NO2 is an intermediate also, you will have to set up a different net rate equation based on this intermediate. So since we have NO3 here, I will set up a net rate equation based on NO3 asterisk. Take note, you will only do that for the intermediate. You won't do that for that species which is not an intermediate. Okay, so now you will go back to all four equations and check where NO3 appears. You have it here, you have it here, you have it here, you have it here, telling you that you will have four terms here in your net rate equation. So in the first equation, NO3 is product. So just like in the first here, it was written as negative because I have placed it here as reactant. So I will have K1 and you will have N2O5. That's for this. In here, it's a reactant, and it's reactant here, so that would be plus. K sub 2, NO2, NO3, asterisk. Okay, I'm always using the reactants. Then, in the third step, it's appearing here, also reactant, so plus K3, NO3 asterisk, and in here, it's also reactant. So this would be the last fourth term. K sub 4, NO asterisk, NO3 asterisk. Okay? You have that. So you have this. Now, you may wonder why set up a net rate equation based on the intermediate. Recall again what was discussed, that the intermediate is decomposed right away to form the final products, or its rate is so very small, its amount is so very small, or rate is so very small that if compared to the others, it's more or less negligible. If that is the case, you can set the rate of reaction, or the net rate of reaction based on any intermediate for that matter, equal to 0. So if you make that 0, this would be the resulting equation. So 0 would be equal to. What I'll do, I will group all the terms that has the NO3 together, and I will factor out NO3 already. So I will have K sub 2, and this is the only one that does not have the NO3. The rest of the three terms has the NO3, so I will have the NO3 concentration here, and I will multiply it, of course, to the appropriate multiplier, so that it will be the same as it appears in the last line that we have written in the previous page. NO asterisk. Okay? Now, this one being negative, you can place it here. And you have NO3 asterisk. Still copy everything. The purpose of this is for you to be able to replace the NO3 in the original equation, and that's equation number 1 by, sorry class, disregard this, by the representation that you have here for NO3. Meaning, I'd like to go back to the first part. This NO3, this NO3 will be replaced by the NO3 that you have here. So you have NO3 asterisk being equal to, so you have K sub 2 N2O5 all over K sub 2 NO2 plus K3 plus K4 NO asterisk. This NO3 could have been substituted right away to equation 1 without the presence of this. But since we still have NO, you need to eliminate this NO, which is another intermediate. How? You set up another equation based on the intermediate NO, or nitrogen oxide. So based on the equations that we have, NO is present in the last two reactions only. I'll go back to the previous page. You can see that NO is present here and in here, but it's not appearing in the reversible reaction. So then you will only have two terms for the representation of NO. And those two terms would be this, negative K3, NO3 asterisk, plus K4, NO asterisk, NO3 asterisk. Okay? This would be set to 0, and you will have, if this is set to 0, because this is an intermediate, so the rate of reaction is 0, this NO3 will cancel out, right? So you will have a negative K3 plus K4 NO asterisk. From here, you can get the concentration of NO asterisk. And that would be K3 over K4. So this would be your equation 3. This equation 3 should be substituted in here. Okay? So if we will substitute 3 to 2, let me borrow just a few minutes. So 3 substituted to 2 will yield something like this. NO3 asterisk now, if 3 is substituted to 2, will be equal to K2, N2O5, K2, NO2, plus 2 K3. Okay, you do that as an exercise at home, so you will also, anyway, this will be uploaded, the video that is. So this would be the resulting NO3 if equation 3 is substituted to 2. If this NO3 is substituted to 1, so if this is 4 already, if 4 is substituted to 1, this will be the corresponding rate based on dinitrogen pentoxide. So it would be K1 N2O5 minus K2 K2 and O2, then you will have this entire expression, K1 and 2O5, K2 and O2 plus 2K3. Hi? By the way, this is K1 class. That's not K2. It's K1. Okay? Now, I see this. I see this being common. So you can factor it out. So you have K1 and 2O5 times. So you have 1 minus. So you have K2 and O2 all over K2 and O2 plus 2K3. So we're here. And this is the rate in terms of dinitrogen pentoxide. You can see? Now, the next will be in the making of the assumption, the very important assumption. What assumption would that be? The appropriate assumption. I'd like to go to the next slide. I'll make a next assumption. So we will assume that since K2 is the reverse reaction of the reversible reaction, it's a lot less in value to K3. If it's a lot less in value to K3, the reaction in terms of dinitrogen pentaoxide would be this. It's a first order decomposition. Why? I'd like to go back to the previous so you will see. If this is very small compared to this, because this is the reverse reaction of the first reaction, a very small value divided by a very big value will be resulting to a very small value. It's like subtracting 0 from 1. So this means this is 1. Like saying this value would be more or less 0. A very small value divided by a big value will be a very small value. So that would be 0. This is 1. 1 times this will yield this final rate law. So this proves that the rate of decomposition really of dinitrogen pentoxide is first order. Okay, that's it. That's how you prove the relationship of the mechanism of the reaction to its provided rate law, or to a provided statement about the rate of reaction. In this case, we're not provided with the rate law. We're the one who wrote the rate law based on the statement that was provided for us. Okay, so should you have any question, just drop me a line in the GC or in Canvas. I have now a class with my calculus and I'm late already. Hopefully you've learned something new today. So I will now stop sharing and share correspondingly later on the recorded video. Bye, class.